This video focuses on the idea of a Venn diagram. Now, some of you, again, depending on your background, you may already have a familiarity with Venn diagrams. This is just a relatively brief video just to introduce the concept of a Venn diagram. Now, probably the best way for me to start is to give you a little analogy. So like graphs are to functions, right? So think about, the graphs of functions that like if I say a parabola, you know what it looks like, and a logarithmic graph, you know what they look like. So you can associate pictures with of functions, which we call graphs. So graphs are to functions. I'll just put this in quotes. What Venn diagrams Venn diagrams are to sets, right? So graphs are to functions. What Venn diagrams, why do I keep messing up my A? What Venn diagrams are to sets, right? So again, the analogy I'm trying to paint here is that a Venn diagram gives you a visual of what a set is. So far our sets have been, very, very abstract. We talk about a universe, and then we talk about elements in the universe and things like that. But at least now it will give us a way to visualize, and it's not just a set, but it actually gives us a really useful way of visualizing the operations along with those sets, right? So basically, the universe, our universal set, is tends to be represented. I'm just using these three lines to say represented by. So the universe is represented by a rectangle, right? And then our set, so like A, B, C, etc. So our sets in our universe, these are represented by circles, right? And so what I'm going to illustrate a couple concepts with first is just two sets. I'm going to use two sets to illustrate a few ideas associated with the Venn diagram, and then just up the ante a little bit and say, well, what does it look like with three sets? So in general, when we have a Venn diagram, so you have a rectangle that represents everything that is being considered, and then you have your sets inside. Now, since the sets A, B, and C are typically subsets of the universal set, they tend to be inside, so strictly contained within the rectangle. Now, the most general way to represent a situation, if you're looking at just two subsets of the universe, is to have two overlapping circles like this, not completely overlapping. And in a second, I'll show you what it means what if one of the circles is completely inside the other one. Well, that's actually related to a concept we looked at earlier. But in general, we don't typically label the universe as U, but when I'm talking about like A and B, if I don't have these labels, then it's a little confusing. So you tend to label your Venn diagrams like that, right? And then so for instance, so what I'm going to do is just use this one and illustrate a few of the operations that we've talked about. And once my little illustration here gets too messy, I'll draw another one and illustrate some more, right? So I'll try to put as much as I can on this one without making it too confusing. So for instance, if I wanted to graphically represent or illustrate the intersection between these two sets A and B, well, it would be the region which they're overlapping, right? So that would be A intersect B, right? If I wanted to represent the union, so now remember what the union is? It's all the elements in A or B or both. So that red region now is A union B. I'll do one more on this. What if I wanted to represent the complement of A? Well, the complement of A would be everything outside the A circle. So everything outside of this one, well, that would include this part of B and then everything still in the rectangle, because you have to be in the universe. So what I'm shading here in green, I'll try to be very careful there and there, not as to go inside. And then like this, that is the complement of A, right? So very easily with just this little picture, you can illustrate, the union, the intersection, the complement. Also, in a previous video, I illustrated a formal way of proving one of the set properties or laws. Well, it turns out you can visualize those properties using a Venn diagram. You can't really use them, let's say, for a formal proof, but you can use the Venn diagrams to illustrate that. So you draw one side of the property and then you draw the other side of the property and then you realize, hey, they're exactly the same. All right. Okay, so let's look at a few more examples of how we can represent things in a Venn diagram. So let me draw another one since I've pretty much colored everything here. And part of the reason why I'm doing a few more examples of this is just that there's actually one other notation that I want to introduce that's related to one of the operations that we've looked at previously. So let's say this is A and B. Now suppose I wanted the elements that are just in B, right? The elements that are just in B, so only B, not A and B. Well, that would be right here. So I'm going to draw that like this. So this, what I've shaded here, so that part of it represents elements in B alone, right? Now let's see if we can, so notice I wrote it out in words here, but let's see if we could represent it using, a combination of one or, two or more of these operations. Well, for sure, the region that I've shaded is outside of A, right? So it's a part of a complement, right? Because there's like none of the elements, or this region here is not inside the A circle. But remember, A complement would include elements not just here, but also outside of both circles, right? But we don't want that. I only want the portion that's shaded inside of B. So I could think of it this way. It's everything outside of A and inside of B, right? So I can represent the elements that are only in, when I'm looking at just two sets, A and B, right? And of course, there's always a universe. if I want to somehow communicate that only the elements in B alone are being considered. So this additional word here, alone, is saying just B. Then I have to take everything outside of A and inside of B. So then this is how it could be represented using the operations that we're familiar with. Now, it turns out there's another notation that is sometimes used to represent this. So this is new, right? Pay attention. What I could say is this is all the elements in B, but then I take out the elements, those elements in B that are in A. So you take out that the elements that are in that overlapping region. And this operation here is sometimes referred to as the set minus. But you can't think of it in terms of numbers. You have to think of it in terms of elements. So you start with everything that's in B, and then you take away those elements that are also in A, right? So let's do an example here just to kind of illustrate what's going on. I'm going to take this to be a simple universe. So 1, 2, 3, 4, 5 is my universe here. And then let me take A to be 1, 2, 3, right? And then I'm going to take B to be 3, 4, 5. So maybe you see what I'm doing here. But let's say this is my universe and these are the two sets. Well, so what I tend to do is, if you want to kind of visualize this in the form of a Venn diagram, I am going to do this. Now, what you could do is start with A and B, and in fact, start with what they have in common. Right. In fact, I'll write those elements in a different color. Well, they have a 3 in common, so I'll put the and only 3. Right. The A intersect B here is a single element 3, so I'll put the 3 there. And then let's say, I didn't label it. Let me go ahead and label it. Let's label this A and B. Let's now list the elements, or indicate the elements in this Venn diagram where they're only in A. So that's 1 and 2. And then let's do the same thing for B, 4 and 5. And then once I have this covered, then I would look in my universe to see if I have any other elements, right? Other than the ones already indicated in the circles. If I had, for instance, a 6 and a 7, I would put it somewhere outside both of them, right? But here, everything in the universe is either in A or B or both, right? So now you could look at it and say, well, what is, to kind of illustrate this new way, this slightly new operation, this B minus A. So the elements in B are 3, 4, 5. Of the 3, 4, 5, take away any element that's also in A. But that's only a 3, right? So then we're left with just 4 and 5. And again, that's that portion of it, right? Another notation that's sometimes used for the set minus is a backslash. So it's sometimes indicated with the typical minus sign, or something like this. I tend to use the minus sign. I have no problem. I understand this notation, and especially in context of sets, you know what it means. But if we have need for this operation in the future, then we're gonna stick with the minus notation, right? So one other thing. So now, what does it look like if you're considering a universe and three subsets of that universe. So let's say A, B, C, right? Let me go ahead and draw something like that. In fact, let me go down a little bit further. And okay, so now if you're doing three, you'd have something like this, and then you'd have to put a third one there. And then, so let's call this A, B, C. And again, now once you go to three, you see you have a lot more regions to consider, right? So I'm only going to do a few of these. So the region here that is common to both A, B, and C, right? If you remember when we were doing our set properties of set operations, we looked at things like what happens if you have to intersect three sets. Well, because of the associative property, I can indicate or I can denote the blue region by this expression, A intersect B intersect C, right? So it's everything in common in all three sets, right? Now, what if you wanted this little red region there that is inside of B and C, but not A? So what if you wanted just that red region there? So again, let me write that out in words first, right? So elements and only B and C, but not A. Well, just saying it out like that, you kind of see what's going on. So you want elements that are in B and C. So I would say it would be B intersect C. But if I just stop there, B intersect C would be all of this. It would be the red and the blue, but I don't want the blue. So essentially I have to say that I have to make sure that none of these elements that the red elements that I'm looking at are in A, and then that would be and not A, right? So all the elements that are in B and C, but not, or you could just say and not A. And then that would give me that little red region. Just to illustrate that concept some more, look at this, just that portion of the Venn diagram with the three elements. So this green region, that represents elements in A and C, but not B, right? So again, if you say it out in words and then just translate it. So, like when you say and, that implies an intersection. When you say a not, that implies a complement. So I want elements in A and C, but not, or you could still say and not B. And then that gives you a really nice way of identifying. So I'll do one more, right? I'll do one more, and for this I need a different color. So let me try orange. So let's say I wanted just this. The orange region here would represent elements only in C, right? Only in C. So C alone, no other set. So that would be C and not A and not B. And in fact, because of the commutative properties, it doesn't matter the order in which I do this. This is the same, all right? Going back to what we previously did in terms of the operations, this is the same. If you want to keep everything like alphabetic, you could say not A and not B and C, right? So you can change the order however you'd like. because of those nice commutative properties. But using those properties and the set operations, it allows us to target specific regions, and we can refer to specific sets of elements, not necessarily an entire set A, but just A by itself, or just B, or different combinations of them, right? So again, the Venn diagram will be one of the really useful tools once we start discussing other concepts that involves not just identifying sets and doing operations with them, but how it might relate to other topics and other concepts. So if you're a visual learner, the Venn diagram is a really useful tool, and it's usually a tool that helps you set up a problem correctly, and then there's more to come. There's always more to come. And on that note, I'll see you in one of the successive videos.